Hello and welcome to Multiparadigm Data Science with the Wolfram language. Section 4, Assembling a Multiparadigm Toolset. The very first section of this course, Building a Project Workflow, provided an overview of the multiparadigm project workflow. Sections 2 and 3 provided more details on functionality useful for the wrangle and explore stages of the workflow. In section 4, we'll continue with the multiparadigm approach and look at different algorithms, techniques useful for the analyze stage of the workflow. The goal is to assemble a multi-paradigm toolset that can be incorporated into the workflow and used to drive it with questions. Instead of restricting ourselves to traditional techniques associated with specific kinds of data, let's reach out across disciplines to use the tool that is most suited to answer our questions. But before we begin, let's quickly review some of the terminology commonly used in data science. These have been borrowed from both statistics and machine learning. For a data sample X, X1, X2, and so on are known as the features of the sample or predictive variables or independent variables. Y is the dependent variable or the response variable or output value or label. The model itself can either be a function with associated assumptions and optimization criteria used to approximate the behavior suggested by the data, or it can refer to a black box represented by an algorithm that takes training data as input and produces predictions of labels and values as output. Parameters are the values in the model that are not assumed by the predictor or response variables. A big part of machine learning often involves learning these parameter values. Training is the process of identifying the function or the algorithm and the corresponding parameters that best represent the relationship between the input and the output. Let's look at a few questions that data science projects often try to answer with the help of data. To begin with, we have one of the most frequently asked questions that is of the type, is this A or B? Or even A or B or C or D or E? In data science, this is known as classification, trying to figure out if a sample belongs to class 1 or class 2. So questions along the lines of, given an image, can we label it as a cat or a dog? Given text of an email, can we say if it's spam or not? For text in different languages, can we label each piece as English or French or Arabic or something else? Can we classify a Facebook post according to its topic, say technology, food, travel? Supervised machine learning is a technique where the algorithm attempts to learn from training examples of input-output pairs to predict output labels or values for new input. Classification perhaps accounts for the widest application of supervised machine learning to real-world problems. It is the algorithm of choice if your problem can be posed as the question, is this A or B or C or D or E, and so on. So it is a descriptive modeling task which tries to predict the class label of a sample based on the previously labeled instances. Here's some training data where each sample has two features, age and income, and a predefined class label, high or low, representing the credit risk posed by the hypothetical individual. This is the target label we'd like to predict for new samples. Using this data, we'd like to infer a function to map from the feature values to a label. And once we have the function, we can use it to predict a label when given the feature values of a new data point. Classify is the machine learning superfunction available in the Wolfram language. It's perfect for the multi-paradigm project workflow as it automates the process of classification. It picks the optimum algorithm internally according to the available data, whether it's numeric or text or sound or images or any combinations of these. The label training examples are used to learn a classifier function that can be used to classify and label new samples. It can also be used to find the probability that the sample belongs to a certain class. Here we see how the probability of the sample belonging to class A changes as the value of the numeric feature changes. Let's revisit the famous Fisher's iris dataset that we worked with in the Get to Know Your Data section. This famous dataset has the recorded sepal length, sepal width, petal length, and petal width of the samples from 3 different species of the iris flower. Given these 4 features, the classification task is to predict the species of a new sample. Here's some training data for us to train the classifier, and some test data to see how well the classifier is performing. A quick visual exploration of the feature shows us that they are well suited for discriminating between the 3 classes of species and can be directly used to build the classifier without any feature engineering. So we feed the training data into Classify. Here are the predicted class labels for 10 random samples from the test data. We can find more details about the classifier that was created, along with the algorithm that was used, decision tree. We can find out the values of the various parameters used for this algorithm. We can see how the training progressed. And what was the performance on the test set? Accuracy shows how many samples had the class labels predicted correctly. It's not enough to just build a classifier. We need to evaluate its performance to see if it's providing reasonable output. This is where the test data is useful. Since we know the labels of these samples, we can match them against the predicted labels to see how well the classifier is doing. Accuracy is one useful measure of performance, giving the fraction of correctly classified examples. The confusion matrix is another useful measure, which shows at a glance how many samples of each class were labeled correctly as belonging to that class or mislabeled as belonging to another class. Classifier measurements can be used to compute a whole range of metrics useful for evaluating the performance of a classifier. We can find examples from one class that were mislabeled as another class. Here are the probabilities from the classifier function, which shows why the mistakes were made. The iris dataset contained only numeric feature. Here is an example where we build a classifier using labeled images of trees as input to predict the species of the tree as output. We see the logistic regression algorithm was chosen and it achieved an accuracy of 89%. All the maples in the test data were classified correctly, but there were misclassifications for eucalyptus, oak, and pine. These were the best classified samples with 100% certainty. And these were the worst classified samples. These are the samples of eucalyptuses misclassified as oaks. Here's yet another example of building a classifier using text input. We import the text from works of famous authors like Shakespeare, Jane Austen, and Agatha Christie. Now let's try to train a classifier on these texts to predict the author when given a sample of his or her writing. A simple Markov model is able to do a good job of predicting the author from a sample of their writing. Classify can be configured to use one of the many well-known classification algorithms as a method. Whether it's logistic regression, nearest neighbors, naive Bayes, decision tree, gradient boosted trees, random forests, Markov models, support vector machines, or even neural networks. Let's compare the performance of 2 different classifiers trained on the same data. One is set to use logistic regression and the other naive Bayes. We see that the decision probability for a sample belonging to class A reduces gradually for the logistic regression classifier, whereas it is a sharp change for the naive Bayes classifier. Classify can also be customized by setting a specific value as the indeterminate threshold so that the classifier attempts to make a confident prediction only when the probability of the sample belonging to a class is high enough. Since we set the indeterminate threshold to a high value of 0.9 in this example, the classifier does not make a decision and instead just returns the label as indeterminate. This can be useful in fine-tuning the performance of a classifier to avoid false positives. Classify can also be customized to assign a specific utility value to each possible pairing of actual and predicted labels. For example, in this mushroom dataset, the classifier tries to predict whether the mushroom is edible or not. Each record is a mushroom sample along with its label edible or poisonous. Once we have trained a classifier, we can compare the predicted versus actual class labels to see how many poisonous mushrooms got predicted as edible. In this scenario, we'd really like to avoid false positives, that is, poisonous mushrooms getting labeled as edible. We can set the utility function to penalize such predictions more than false negatives, that is, edible mushrooms being classified as poisonous. We'd also like the classifier to declare labels as indeterminate for decisions that are not clear, so we set up a utility function as seen here. The new classifier trained with the utility function predicts many more samples as indeterminate, but also has fewer false positives. Lastly, we can tune the performance of the classifier by setting a performance goal. A classifier's performance can be optimized for training speed, actual runtime speed, memory usage, or accuracy of predictions. Here is a comparison of the training times of two classifiers with different performance goals. Naturally, the training time of the classifier whose performance is being optimized for accuracy takes longer to train. In summary, we looked at classification as a supervised machine learning task for predicting labels for new samples with the help of a set of previously labeled training samples. We applied the machine learning superfunction classify on various datasets with numerical features, images, text, or even combinations of different types. We use classifier measurements to evaluate the performance of the classifiers, and we looked at different options available for customizing Classify to suit the need for the task at hand. Among them, method to use a specific classification algorithm, utility function and indeterminate thresholds to control predictions, and performance goal to optimize performance according to different criteria.